we are going to take a look at what an identity matrix is, and please remember we are going to, the context is square matrices only. I have not yet figured out whether identity matrices exist for rectangular matrices or not, so we are not going to even talk about that. So what is an identity matrix? I am going to write examples of identity matrix here. Matrices. All of these are identity matrices. So what's really special about an identity matrix? Now look at the diagonal of each matrix, what is called as the principal diagonal of a matrix, of a square matrix. So you start from this element and go right down here. Okay, this is the diagonal. This is the principal diagonal. This is the principal diagonal. So an identity matrix has ones along the PD, principal diagonal, and all other elements are 0. All other elements, see, look at it. These are 0, these are 0, these are 0, these are 0. So that's an identity matrix, a square matrix which has ones along its principal diagonal and all other elements are 0. Okay, very good. So I think we saw what a, and really, this is 2 by 2, this is 3 by 3, this was 4 by 4, but you can go all the way up to m by n. And the same rule applies, ones across the principal diagonal. Okay. The notation for an identity matrix is I. So I is equal to 0, 1, or the other 3 by 3, 4 by 4, etc. So the notation for an identity matrix is I. Now, what's so special about an identity matrix? Okay, what's so special about an identity matrix? The one important property, the important property of an identity matrix is that you take any square matrix, let's say A, and you multiply it by I, you get the same matrix. So the matrix is unchanged, so it's kind of like, with just plain numbers. That's the property of 1. You multiply any number by 1, you get the number itself. Now in multiplication, it works the other way around too, right? Because multiplication of numbers is commutative. How about this case? Now we saw earlier that in the case of matrices, and again we are talking only about square matrices, if you have a matrix A and a matrix B, then this doesn't work as a rule. Okay, so we have already said to ourselves and demonstrated to ourselves that matrix multiplication as a rule is not commutative. It is not commutative. A multiplied by B not equal to B multiplied by A. But in the case of identity matrices, there is an exception to that rule. Okay, multiplication of a matrix by its identity matrix is commutative. Now, we have said this, but why not quickly demonstrate it to ourselves with an example, sample matrix, right? So let's say A equal to 1, 2, 0, 3, okay? And I am going to multiply it by the identity matrix. Let's see what we end up with. We have done matrix multiplication quite a bit. So let's see, okay? 1, 2, 1, 2. So that's 1 plus 0, 1, 2, 0 plus 2, 0, 3, 0, 3. 0, 0, 3. 3. That gives us 1, 2, 0, 3. So indeed, A multiplied by I has given us A. Let's try the other way around. 0, 1 into 1, 2, 0, 3. Let's calculate this. So this is 1, 0, 1, 0. We get a 1 here. 1, 0. We get a 2 here. 0, 1. So we get a 0 here and 0, 1 applied here. 0 and 1, 3. 1, 2, 0, 3. So this was I into A, and it's actually given us A, right? So we just demonstrated to ourselves, at least for one matrix, that AI equal to IA equal to A. So multiplying a matrix by the identity matrix leaves the matrix unchanged. So we just demonstrated it for one matrix, but it really is true. Okay, and you know what I want to do? I want to do a deeper justification of why this is the case. Let's see how. Okay, let's see how. So instead of taking a specific matrix, I am going to take A to be A, B, C, D. These are real numbers, okay? And I am going to multiply it by the identity matrix. Okay. So if we can kind of convince ourselves about this, and on the other hand, we are going to look at 1, 0, 0, 1, the identity matrix into A, B, C, D. Very good. And here we are going to put to good use all that we learned about matrix multiplication. Okay. Now, I hope you remember the whole columns method of multiplication of matrices. That's what we are going to use. So what I am going to do is, the columns of this matrix, I am going to write them out as many number of times as the number of columns here, which is 2. So just to show you what I mean, and you'll recall this from our matrix multiplication videos. C, D, A, B, C, D. Okay. Now if you remember, I take this column 1, 0 and twist it around 1, 0, and then I take this column 0, 1 and I twist it around 0, 1. This is the way we did the whole columns method of multiplication, and you'll quickly see that we now have these. This is one column because it's really a linear combination. It's an addition of scalar multiples of these matrices. So we have two columns. In one of them, CD is going to zero out, and the other one, AB, is going to zero out, and in one, AB is going to stay, and the other one, CD, is going to stay. So what you are really going to end up with is A, B, C, D. That was quite obvious, isn't it? But the whole columns method, that's why we spent so much time on the matrix multiplication videos. The whole columns method here gave us a very good view of why, when a matrix is multiplied by the identity matrix, wherein the identity matrix is the multiplier, we end up with the matrix itself. Now here, we are going to use the whole rows method, right? The whole rows method. And what was the whole rows method? So I take the rows of this matrix, AC, BD, and I write them as many times as the number of rows here. AC, BD. And what do we do now? We take this row and twist it around to make it vertical, 1, 0. And then we take this row and do the same thing, twist it around to make it vertical. the other thing is happening here because we are working with rows now. Okay, here in this row, the upper row of the result matrix, BD is going to get zeroed out, and here AC is going to get zeroed out, whereas here AC is going to stay unchanged and here BD is going to stay unchanged, and hence what you are going to end up with is ACBD. Okay, so I think we more or less, I don't know if this is a proof, but we have convincingly and in a very generic way convinced ourselves that a matrix multiplied by an identity matrix or the identity matrix multiplied by the matrix give us the matrix itself. A into A is equal to A. You can try it with 3 by 3 matrices. You can apply the whole columns method, the whole rows method, and I think the principles are the same. So you are going to get the same result. Okay. Anything else that is special about an identity matrix which might come in handy? Let's take a look. Okay. So this is your identity matrix 1 0 0 1. Okay. This is 2 by 2. Now take a look at the column vectors 1 0 0 1 and think of them as vectors. And this is a 2 by 2 matrix, so I take you to 2D and you'll realize that this vector is here and this vector is here. So the column vectors, the columns of the identity matrix in the respective vector space give us n vectors along the axes, right? So this one is horizontal, this one is vertical. If you were to take the 3 by 3 identity matrix, and I were to just represent R3 here, okay, I'm saying this is X positive, Y positive direction and Z positive direction, and you look at these 3 column vectors, right? The first one will be here, the second one will be here 0 1 0, and the third one 0 0 1 will be here. So just pointing this out, I don't think we are going to put this to any use, but be sure this will come in very handy. So I think we took a good look at identity matrices. Let's just try to write down what we learned for an identity matrix. Notation is I. Okay. What is an identity matrix? A square matrix with ones along its principal diagonal and zeros in all other positions. Okay, if you multiply any matrix by the identity matrix, and of course, we have learned matrix multiplication, so the orders are the same. The result is the matrix which remains unchanged, and if you multiply the other way around, if you have the identity matrix as the multiplicand and you multiply the given matrix to it, you are left with the same result. I don't think we really called out any other properties. We also saw why AI leaves A unchanged. We did the thing with the column vectors. we saw the column vectors picture, and here we saw the row vectors picture. I just wanted to for us to spend some time on the identity matrix, because it is a very important building block when we come to inverse of a matrix, which is probably the next video I do. Meanwhile, I would encourage you to experiment. Take any matrix 1, 3, 2, 5, 0, 1, multiply it with the identity matrix and convince yourself that you get the same matrix. And you can also do it the other way around. You can put I in front here, multiply, and make sure the result is the same matrix. If for no other reason, do it to practice matrix multiplication. I think I'm going to stop here. I hope this was useful.